All right, so welcome back from break. We've only got 2 weeks left of class. After that, we've got a week of finals. There is a final exam in this course. The content has been set, or at least the draft of it. More details will be released either this week or later this week or next week. But there are two parts to it. We do know that there are going to be about 20 multiple choice questions, and then there will be a programming part. That you'll probably be given, all of that you'll probably be given about 24 hours, just like the rest of this stuff. It'll be designed for about two hours, like the usual final exam, but we'll do it asynchronously so that physical attendance is not required, just like the other three. But in any case, the next 2 weeks, you'll have opportunities to redo one hack and one lab from hacks 5 through 12. 12 is, of course, due today. And all you need to do is is read the Piazza post for details on how to do that. You'll be going to your actual lab or hack session and getting signed off on those. All right. So, to remind ourselves, because we were gone for a week, of where we left everything off, remember that we were looking at at linear search, and then we looked at binary search. Binary search offered an exponential speed up because it exploited the fact that everything was sorted. And so if everything is sorted, all you need to do is jump to the middle element, right? And if that's the thing you're looking for, great, you're golden. But otherwise, if that's not the thing that you're looking for, then you either search in the left half of the list or you search in the right half of the list. In either case, you've cut the input size in half. Doing that over and over and over again leads to a logarithmic behavior, a logarithmic number of comparisons. I meant to, yeah, there we go. Yeah, there we go. So what I want to do now, though, is switch gears, because binary search, of course, required that everything be sorted, right? So that's where we're going to pick up where we left off. All right, we're going to look at one sorting algorithm called selection sort. It's the one that we kind of simulated at the end here, where we looked at this array here of I think there are 8 elements in there, yes. And what we did is we went through and we found the minimum element. In this case, it was 2 right there. And then what we did is we put it at the front of the list, or the array in this case. Then we went through the remaining elements and we found the next smallest element, 3. Then we did that again, found the 3rd smallest element, the 4th smallest element, the 5th smallest element, et cetera, right? Until we got down to the last element, which was already where it needed to be. Now, what I want to do is I want to think about that in terms of how we can actually implement this and see. We'll think about it in general terms here, and then we'll try to pick up a pattern that we can actually, implement. So here's that same array that we used before. Now, what we're going to do on this first iteration, so let's keep track of iterations. Iteration 1. The first iteration, we're going to search elements indexed 0 up to n minus 1. I'm keeping it general automatically here, right? This is 0, 1, 2, ... This is n minus 1. Now, obviously, that's going to be 7 because n is 8 in this case, but I want to generalize this algorithm so that we can actually implement it, okay? We're going to search these elements for the minimum, right? And then place it at index ... So where does that first element go if it's going to go in the first index over here? At index 0, right? Now, let's look at the second iteration here. Oh, by the way, what does it mean to place it at index 0? How do we actually physically go about doing that? Well, that's the element right here, right? So I've written off 2 to the side here temporarily, right? I need to put it where? I need to put it right here. But that cell is already occupied by 6. So what should I do with 6? Swap it. Put it over here, and then I can put 2 there, right? It's done. So what I'm going to do is I'm going to highlight this as being sorted. Done. Okay? And 6 is over there where it needs to be. So let me revise this. Place it at index. Let's go ahead and say that we're going to swap it. Swap it with index ... 0. Okay? All right, great. Now let's go with iteration 2. Am I going to be searching all of the elements here? No, because I've already taken care of the first one. I'm going to be searching these elements right here. I'm going to be searching elements 1 through n minus 1. Right? Find the minimum among those and place it where? At index 1. You can fast forward here and see the pattern, right? We're going to search elements to index 2 through n minus 1, and we're going to swap it with element at index 2. Okay? Dot, dot, dot. Let's go ahead and generalize this. At some iteration, right, I'm going to be searching in elements I through n minus 1 for the minimum, and I'm going to place it at index I. Okay? That's some iteration. We're going to come back and fill that in here. When do I stop? All right? So let me fast forward here, right, and go ahead and oops, I don't want to get rid of all of it. Let's go ahead and fast forward here. And, oops, what are the elements again? 3, 3, 4, 5, 6, 9, 9. 3, 3, 4, 5, 6, 9. And now we are at the second to last iteration. All of these have been sorted. I'm highlighting them in green really quickly here. All right, 9 is right here, but it is not yet sorted. Do we need to consider it, though? In this particular case, 9 is already where it needs to be, but in general, it's also going to be where it needs to be. Because if you sort the first, if you've got 10 elements and you sort the first 9 and place them where they need to be, where's that 10th element? It's where it needs to be. So how many iterations do I go? I don't go n iterations, n elements. I go only n minus 1 iterations. And I search elements n minus 2 through n minus 1. In other words, 2 elements. I find the minimum, and I place it where? At n minus 2. Right? So now let's think about this more generally. Right? We've got elements here, and I'm thinking about the ith iteration. I'm thinking about the ith iteration because I'm going to be using the index variable I in my loop for I equals something through something I plus plus. Right? Elements I, or 0 through I minus 1 have all been sorted. Dot, dot, dot. These are all sorted. Okay? Now I'm thinking about elements I through n minus 1. Dot, dot, dot. These are unsorted. And you need to find the minimum value from elements I through n minus 1. That's my generalization. I runs from 0, 1, 2, dot, 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 all through n minus 1. All the way up to and including n minus 2. You find the minimum among all of those elements, and you swap it with the element at index, the same index that you've got here that you start at, right? Swap it with index I. You find the minimum, right? And then you exchange it with whatever is at the beginning. Understanding that, let's go ahead and write a selection sort implementation in C. So first of all, it's going to be a void function. Why? Because I'm not returning anything. I'm going to call it what it is. It's selection sort. And by the way, why is it called selection sort? Each iteration you go through and you select the minimum, and then you put it where it needs to be. Right? It's not any fancier name than that. Can I use const int star for my array? No. Why? Because I'm going to be making changes to it, right? In particular, I'm going to be swapping elements around and sorting it. So there's my array. I also need to be told how big the array is in n, right? Okay. Now, that outer for loop, where I'm doing these iterations right here, right? Iterations 1 through n minus 1, I'm going to be achieving that with index values 0. I runs from 0 up to n minus 2. That's a little bit different than our idiomatic for loop. An idiomatic for loop would look something like this. For int I equals 0, I is less than n, I plus plus. Right? I don't run all the way up to and including n minus 1. I run up to and including n minus 2, and because it's strictly less than, n minus 1 gets me to n minus 2. Now what I'm going to do is I'm going to find the minimum among elements array sub I through array sub n minus 1, the last element. Right? And then I will swap the minimum element with array sub I. Right? Help me on this. Find the minimum elements among those elements. Right? What does that kind of tell you? What more do we need now? Another loop, right? So let's go with another for loop here. For int, can I use I again? Nope. I have to use, well, what comes next? J. We're not that creative, right? Don't get fancy, right? For int j equals something, we're going to start somewhere. J is less than something, we're going to end somewhere. J plus plus. Right? So if I want to find the minimum elements among I through n minus 1, well, first of all, I need an index variable to keep track of the minimum, right? Because if there are 5 elements here and, okay, well, this is the minimum so far. But down here, I find something that's even less, right? I want to update what I am referring to over here, right? So what I'm going to do is I'm going to establish another variable here called min index, right? Always, always, always initialize your variables. What should I initialize it to? 0? All right. Where is the index 0, though? All the way at the beginning, right? I could do that, but then I would always be comparing elements I through n minus 1 to that first guy. And that first guy was already the minimum, right? He's always going to be less, right? Well, if you're going to start your search at I, why don't you start your index at I? Right? Now, what should I run my j from? Right? I'm searching elements I through n minus 1, right? So if I started at I, what am I going to do on that first iteration? I'm going to end up comparing it with itself. It's kind of pointless, right? So where should I start it? I plus 1, the next guy over. So I plus 1. What do I go up to and including? N minus 1, so there, that is going to be idiomatic. I go up to 1 less than n, strictly less than n. Okay? N is the full size, exactly. Right? And now, if the element at the j, or if the jth element, if array sub j is less than what I've found so far, min index, right? Then I've found something even smaller. And so I will update my min index to be j. Okay? Once I'm done with that inner for loop, I have found the minimum element. The min index is referring to the minimum element. I need to swap that minimum element with array sub I. So let's go ahead and create a temporary variable here. I'll put in array sub I. That frees up array sub I to take on the value array sub min index. Right? And now, since I've moved it over, array sub min index will take on that temporary value. Right? There. You can have a return statement here. Even though you're not returning anything, it's a good idea to put those in, even though they'll be provided for you. Right? So let's go ahead and see, make sure that this is working. There we go. I've got an array here that's unsorted. Here's the version that we sorted by hand. Let me go ahead and get rid of this for now, and we'll come back to that. We can search for a key, but only if it's sorted. I'm going to go ahead and print it out to see that it's unsorted. Then I'll call selection sort on array, and then I'll go ahead and print it out again to verify that it indeed has been sorted. Okay? GCC demo. And, oops, print array. Do I not have print array in here? Thought I did. Print array, there it is. Why are you not printing then? Oh, what else do I need? The size, and the size, and the size. There we go. All right, let's go ahead and run it. And there's the original array. And now the array has been sorted, and my binary search will work. We found element 2 at index 0 of the sorted version. Okay? Cool. So how good is this algorithm? How good is this implementation? what I want to do to test that is what I've done is I've imported some code here from Lab 7 or something like that that randomly generates an array of a certain size. Okay. So what I'm going to do after all that's been done is I'll reset n here to be, say, 100. Right? 100 elements. And I'm going to go ahead and create a new array. I'll just call it BUR instead. Right? And random array of size n. Right? And then I'll go ahead and selection sort it. Right? BUR. I'm not going to print it out because I know that it works already. Right? And if I'm going to print out 100 things, and I'm going to make this bigger and bigger and bigger, I don't want to look at 100 things. I don't want to look at 1,000 things. Yeah. Thank you for n. There we go. All right. All right. So how good is this? In other words, is this going to be fast or is this going to be slow? Is this going to be efficient or inefficient? Seems pretty fast to me, right? Let me go ahead and print something after I'm done here. Printf, done, right? End the line. Just so that we get some feedback here, some visual cue that the selection sort actually worked, right? All right. Well, that went by in a blink of an eye, right? Yep. Let's go ahead and bump it up to, I don't know, 1,000? All right. Well, that didn't seem like there was any difference there, right? All right. So, good. Ship it. Right.
No, it's not showing that you did BR at all.
Sorry. No, it is sorting. It's just that I'm not printing it out, right? I could print. Let's go ahead and bump this down to, I don't know, 50, right? And print it out, and show that it is indeed, sorting. Right? I don't know what it was before. It was random, but oops, what have I done wrong? Random array of size R should be 50.
After a while, it just stopped talking.
Oh, thank you, BR. Printing the wrong thing. There we go. There. So 2, 11, 11, 15, 15. Right? It looks to me like it's working.
Yeah.
Right? What I'm interested in now is it efficient? Right? Well, if I'm going to bump this up to 1,000, I don't want to see it. I just want to know, is it fast? Right? And it's fast. Right? What if I bump this up to, say, 10,000? Did you notice it? Small little bit of latency there. Right? Well, try to predict 100,000. Is it going to be just a little bit more latency, or
About a full second.
1, 2,
Or more.
3, 4, 5, 6,
Exponential.
7, 8, 9, 10 is about what I expect, and a couple more. Not very scientific. We can make it a little bit more scientific by running it through this utility called time, a.out. Right? Now that'll actually time it and produce a report that says this is how much user time it took, this is how much system time it took, etc. And it's going to come up about 12 seconds here, I think. There we go, about 12 seconds. Remember, for 100,000. 1 million.
Well over a minute.
All right, we'll go ahead and let that run in the background while we figure out what's going on here. Right? Probably more like 20 minutes. Right? Let's understand why. Okay. So what I'm going to do is I'm going to copy down this selection sort algorithm. I'm going to simplify it into like a little bit of pseudocode here. Right? So and don't worry, I'll bring back the pad here in a second. I wanted to go ahead and look at the for loop here. The for loop runs for I running from 0 up to n minus 2. Right? N minus 2, why? Because it's strictly less than n minus 1. J runs from I plus 1 up to n minus 1. And then you're doing something in there. Right? What are you doing? What are you doing on line 79 through 80? Well, you're doing an assignment on line 80, but is line 80 always executed? Not if the if statement is false. But the if statement always executes. What are you doing in the if statement? You're pulling something out of the array, and you are comparing them. So, just like with linear search and binary search, our measure of work, our resource measure here, is going to be the time that it takes to run this comparison. One comparison is, of course, milliseconds, right? But if I'm doing thousands of comparisons, millions of comparisons, times that millisecond, it starts to become noticeable. How noticeable, though, right? So I'm doing one if comparison, right? X, Y, right? So let's count up the number of comparisons that is being done in the selection sort algorithm here, right? Again, this is the outer for loop, this is the inner for loop, and I've simplified it because I want to look at this from a mathematical perspective, right? There are lines here, 1, 2, and 3. So the question becomes, how many comparisons? We'll start on the innermost part and then work our way out. So on line 3, how many comparisons do I do? If you just look at line 3, how many comparisons do you end up doing? One. Right? Now that box, that loop, or that control structure there is inside of a larger box on line 2, right? So on line 3, you're doing one comparison. How many comparisons are you doing inside the entire box encapsulated by line 2? Well, you're doing it for I plus 1 up to n minus 1, right? How many ones is that? That's going to be 1 plus 1 plus 1 plus dot 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 plus 1 plus 1, right? So if I add those ones up, how many ones are there? It might help to associate each one of those with the index values right here. I plus 1, I plus 2, I plus 3, dot, 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 I plus 2, I plus 3, dot, 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 all the way up to and including n minus 1, and what comes before that? N minus 2. So what is the grand total here? Three? Right? Well, it's going to be generalized, right? It's going to be in terms of I and N. Right? What if I wrote it out like this instead? Everybody can do this. 1 plus 1 plus 1. If I started at 1, 2, 3, plus dot, 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 plus all the way up to n minus 1, and then n. Oops, just 1's up there, sorry. 1 plus 1, n minus 1, and n. There we go. Now how many 1's are there? N, right? N 1's. Right? And so for a grand total of n. Right? I'm not counting them all, am I? I'm starting at I plus 1, and I'm only going up to n minus 1. So let's revise. If I skip that last one, now how many 1's are there? N minus 1. All right? Now if I skip the first I of them, 1, 2, 3, sorry, dot, 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 to I, and then I plus 1, dot, 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 right? How many 1's are there here in this section if I go from 1 up to I? I. Right? So if I took off all those 1's from the grand total, which is n minus 1, how many are there? There you go. Right? So how many are here? N minus, and I'm going to put the I next. I minus 1. Right? Commutativity, I can go ahead and shift those around. Okay? Now the last question will be, how many times do you do that inner for loop with respect to the outer for loop here, running from 0 up to n minus 2? For that, let me establish a full summation. The outer for loop runs I, running from 0 up to n minus 2. And remember that the inner for loop executes n minus I minus 1 times. All right? Now, before we go on, are we all familiar with sigma summation notation? Yes? Okay. Good. So, what I need to do is I need to solve the summation. I could take it and I could put it into a Wolfram Alpha and I could be done with it. But let me go ahead and do at least a little bit of math here today. All right. So the sum of summations is equal to the summation of sums. I've got n plus a negative I, right? That is a sum, plus a negative 1. So I can break this up into 3 summations. I running from 0 up to n minus 1, or sorry, 2 of n minus I running from 0 up to n minus 2 minus summation of 1 of I running from 0 up to n minus 2. Right? Now at that point, hopefully everybody can solve this first one. This is just n plus n plus n plus n. How many times? I is running from 0, 1, 2, 3, 4, all the way up to n minus 1. So because you start at 0 here, how many summations do you actually do? N minus 1. And each time you add an n, so it's n times n minus 1. There we go. Stop at, but include n minus 2. Mathematicians are inclusive, right? Because why? Because they do one indexing, right? We do 0 indexing. The second one, I'm not sure about that one yet, so we'll come back to that. But don't lose it. Now, what about that third one? That's 1 plus 1 plus 1. Again, how many times? Exactly the same as before. N minus 1 times 1 is n minus 1. There. Okay? So it all boils down to solving this summation. Let's go ahead and do it on another one, on another piece of paper, virtual paper, e-paper, whatever. I don't even know what you call this. It's just a tablet, right? All right. So what am I going to be doing? 0 plus 1 plus 2 plus 3 plus ... plus n minus 1 plus n minus 2. Well, first of all, what about that first one? Does it really matter?
Nope.
Nope. So what I'm going to do is I'm going to go ahead and get rid of it and change my summation down here to start at 1. Right? And I can move this stuff over now that I've made room for it. There we go. So has anybody seen this before or something like this before? Yeah, Gauss, right? And 200 years, 300 years ago or something like that, came up with the following, that the sum of natural numbers, 1 plus 2 plus 3 plus 4 up to n, has a closed form solution of the form n times n plus 1 all over 2. Right? And it's might be apocryphal here. It is apocryphal. And the story goes that he came up with this when he was a kid, that his tutor or his teacher or something he was annoying him, so he said, all right, go off in the corner and sum up the numbers 1 to 100 for me. All right, give you some busy work to do. And he immediately came back with 5,050. Well, how did he do it? He came up with this formula. Plug in 100 there. 100 times 99 divided by 2 gives you 5,050. Right? You can do it with any natural numbers. Yeah, exactly. Again, it's probably apocryphal. It probably didn't happen. But that's not what we're doing here, right? We're not going all the way up to n. We're only going up to n minus 2. So all you need to do is take n minus 2 and plug it in over here to these two. And this one is equal to n minus 2 times n minus 2 plus 1 all over 2, which simplifies to n minus 2, n minus 1 all over 2. Right. Now, this is an extremely useful summation that you'll be using over the next couple of years just to do algorithm analysis. Why? Because it pops up all the time because you've got a for loop within a for loop. Anytime that you have that, that's screaming out to you some sort of quadratic, expression, probably apply Gauss's formula and you're done. Right? It actually came up this weekend that's last week I was bored, and so I was doing some Advent of Code stuff. There was one where you had to optimize these fish, or had to be lined up or something like that. On the second part of it, the objective function ended up being Gauss's formula, and if you knew Gauss's formula, all you had to do was go back and change one line of code, apply the formula, and you were good to go. If you didn't know the formula and you did it brute force, then it was not feasible. It was going to end up taking way too much time. But I immediately saw, oh, that's Gauss's formula. All we have to do is do this, right? And n times n plus 1 all over 2. Right? So it does have practical applications, such as getting stars on adventofcode.com. Right? So let me come back over here and, well, actually, let me cut and paste this, because I don't want to rewrite it. copy. There we go. And, oops, paste. There we go. There. All right, so in total here, we have n times n minus 1 minus that thing, which is very similar, n minus 1. All right, this is basically half of this, dot, dot, dot. All right, solve this at some point, and you'll come up with something that looks like this. 1/2 n plus dot, dot, dot. All right? You can throw it into Wolfram Alpha and get an actual solution if you want. I'm not interested in that. What I'm interested in, sorry, n squared there. What I'm interested in is this guy sitting out front here. All right? All these lower order terms, go ahead and ignore them. Why? Because think about what you're doing. You're capturing the idea of work. N is the size of the array that you are trying to sort. You're sorting from, an array of size 10, 100, 1,000, 1,000,000. In other words, n is increasing towards infinity. If n is increasing towards infinity, do any of these lower order terms matter? This minus 1 down here, or maybe there's a linear term in this over here somewhere, right? Does it matter? No. What matters is this highest order term right here, right? Now, the second thing that I'll ask is, does this 1/2 matter? In a sense, in an engineering sense, yes, right? If you want to get an actual pinpoint answer for the behavior. But take this algorithm that is still running, by the way, right? Yep. And move it over to hardware that's twice as fast. What happens to a hidden constant out front here? Let me go ahead and make this a darker green so we can actually see it, right? There's some constant out here that is capturing the idea, that is capturing the idea of the number of seconds it takes to actually perform a comparison. If that's 0.1 nanoseconds, or it's half a nanosecond, or it's 50 nanoseconds, does it really matter? It's some C, right? Move it over to different hardware. The algorithm didn't change, the hardware changed. It'll be faster, yes. You upgrade your, I just had to make sure that the computer worked for this weekend for a VR showcase, but we have a 2080 Ti in it. Now they're up to what, 4080s? Did they drop the Ti stuff though? Is there a 4080 Ti? 4090? Okay. All right, whatever we're up to now, right? It's been 5-6 years or something since the 2080 Ti's that we got ours, and they're 50 times faster. Well, that just means that this is 1/50 now. Well, go ahead and take that 1/2 and incorporate it into your 1/50. The takeaway here is that this is the highest order term, n squared. Okay. Now let's do the same thought experiments that we did with linear search and binary search, where we said, all right, well, if we've got an input size of n, and it's taking n squared time, right? What happens when we double the input size? How much time does it take now? 2n squared, which is equal to 4n squared. In other words, when I compare these two, this is 4 times bigger. Right? 4 times slower. 4 times as many comparisons. All right? So let's come back over here, and I guarantee you this will not execute within the class time here. So let me go ahead and kill it. Right? And let's go back and change the value here to something more manageable. What did we do? 10,000. Let's go with 10,000. What was 10,000? Do we remember? Oh, okay, 0.12 seconds. There we go. All right. That was. Oh, that's only 10,000. So now let's go up to 20,000. I've doubled the input size. Okay. Oops. I didn't compile it yet, though. All right. Now, before I run it, predict. From our analysis on the tablet, it's going to be 4 times as slow. It says that it takes an eighth of a second now. So how many seconds should it take for 20,000 if our analysis was correct? About half a second. Almost dead on. Right? What if we doubled it again to 40,000? recompiled. If our analysis is correct, what should it take now? 4 times 1.5 second is going to be 2 seconds, right? 1, 2, almost dead on. Right? So let's take this and go back down to 10,000 GCC and remind ourselves that it takes about 1/10 of a second, 1/8 of a second. Now let's go back up to that 100,000, right? 1 million. Oh, here, 100,000. That's reasonable. We'll go ahead and run that in the background. And while we're 10,000, I want 100,000, sorry, GCC. And while we're waiting for that, let's come over here and do the same thought experiment, but instead of going from n to 2n, we'll go to 10n. An entire magnitude greater. Right? What's that going to be? 10n squared is going to be 100n squared. In other words, 100 times slower. So if it took 0.1 seconds before, how long should it have taken now? Or 0.12 seconds now? 12 seconds. So now, the one that I killed that we couldn't actually get to run within the 5-10 minutes that we did, right? Tell me, how long would it run if we just let it keep going? 100 times 12 seconds, that is. So 1,200 seconds. 1,200 seconds is, no, 20 minutes, right? So I'm not going to let that go, right? We're going to kill that, okay? That's a lot of minutes, exactly. That's a lot of minutes, but is it a lot of data? 1 million integers? That's nothing. That's less than a megabyte. You can't sort a megabyte of data in less than 20 minutes, right? It's not 1980. What's going on here, right? What's going on here is that this is a terrible sorting algorithm, right? N squared is not an acceptable algorithm at all. What we need is we need a faster algorithm. We need a quicker algorithm. We need quicksort. All right? So now with the remainder of our time today, we're going to introduce the idea of it, but we're not actually going to program this, right? Instead, we're going to wait for Wednesday and show you how you actually do this stuff in practice, because you don't write your own sorting algorithms. You don't write your own searching algorithms. You use the standard libraries, okay? So here's quicksort. What was the array that we had before? Here we go. That's kind of messy, but I'll go ahead and do it. Oh, wait, no, it's already sorted, darn it. Okay. I'm going to have to pull out my random number generator here. 4, 7, 3, 2, 8, 1, 9, 1, 2, 3, 10. There we go. All right, there's my array. So here's the idea. 1, I'm going to choose a pivot element. The first one. So here's my pivot element. I'm going to go ahead and go with green. There we go. Now what I'm going to do is I'm going to partition around the pivot element. What it means is I'm going to what is a pivot element, right? I'm on my I'm pivoting around my axle on my chair right now. Now basketball season has started, so it's traveling if you've got a pivot foot and you lift up your pivot foot, right? The pivot foot means that your foot is down. You can move around that foot, but you can't pick it up off the ground, right? You can slide it around. Can you slide it around? People do, right? No, traveling never gets called anyway, right? So, but anyway, you're going to pivot around this element here, meaning that I'm going to put everything that's greater than the pivot element over here on the right-hand side, right? 7 is greater than 4, so it goes over here. 3 is less than 4, so it's going to go over here, right? 2 is less than 4, so it also goes over here. 8 is greater than 4, so it goes over here. 1, 9, and 10. Right? And then where does 4 go? Right here in the middle. Right? Now tell me, everything on the left-hand side, it's not sorted yet. Everything on the right-hand side is not sorted yet. But what about 4? 4 is where it needs to be, right? Don't move it. You're done with 4. Now what you're going to do is you are going to recurse. Recursion, right? You will apply the exact same algorithm that I just did on this subarray over here, the exact same algorithm that I just did on this subarray over here. Recurse. Recurse. Right? When do you stop? For example, in the next iteration, our pivot element on the left-hand side here is going to be 3, right? So what is it going to look like? 2 goes over here, 1 goes over here, 3 goes over here, and it ends up being where it needs to be. The left partition is going to have 2 elements. What about the right partition? 0 elements. What if a partition has 1 element? 0 elements or 1 element? Do you sort something that's do you sort an array that's of size 1? No. Do you sort an array that's of size 0? No. So that's when you're done, right? You continue this process down until you get down to 1 element. Okay? Now again, we're not going to go through the implementation of this, and we're not going to go through the full analysis of this because it requires analyzing recursive algorithms, et cetera, et cetera. I'm just going to give you the end result, right? Quicksort makes n log n comparisons to sort an array of n elements. Right? That's much, much better than n squared. How much better? Let's go through the same thought experiment, but with n log n instead. Okay? And by the way, I'm going tilde here. It's about n log n. In the worst case, quicksort can devolve into selection sort or insertion. Selection sort. It's not that likely. In the average case and the best case scenario, it's going to only make n log n comparisons. And remember, log n is base 2. Why? Because we're computer scientists, right? We think in binary, all of our bases are 2. Right? So now, same thought experiment here. If the input size is n, and we double it to 2n, before we do it, we're doing n log n comparisons. Now how many comparisons are we making? 2n log 2n. Now, pull out your algebra hats and tell me how to simplify that. What happens to that log 2n? I can split it up. How? Log of AB is what? Log of A versus log of B. What do I do to them? Add them. So log of n plus log of 2. All I did was switch them around. Right? 2 goes over here, n goes over here. And I've got parentheses here to make sure that it's still mathematically correct. Now tell me about this guy right here. Log base 2 of 2 is equal to 1. So this becomes 2n log n plus 2n. In other words, the original is going to be twice as big plus this linear factor down here. For the same reasons that we were kind of ignoring the lower order terms down here, right? And we only focused on the highest order term here, we're going to do the same here. And I'm going to just go ahead and simply say, by fiat, forget about that. Right? And focus just on this one right here. How much bigger is it now? We went from n log n to 2n log n, so it's going to be twice as slow. Twice as slow, right? Or twice as many comparisons. And I'll hedge my bets here and just put about in front of it. About twice as slow. In other words, it's kind of like linear search. Right? In fact, there's a name for this. It's not quite linear. It's quasi-linear, right? Almost linear, quasi, right? So quasi. What's another word with quasi? Say what? Sort of. Yeah, sort of. I'm trying to think of another word that has that as a prefix, though. And other than Quasimodo, I don't know. Well, Quasimodo literally means nearly a man, right? Quasimodo, the character, the Hunchback of Notre Dame, etc. Right? Anyway, go ahead and read a book. Right. All right, so it's twice as slow, right? That's way better than, say, 4 times as slow, right? And when we bump this up to 10, then the difference between these two is even more apparent. It's still only going to be quasi-linear. It's only going to be 10 times slower, not 100 times slower, right? So it's almost linear, right? And in fact, we're going to see the difference when we actually run this thing. Again, I guess I never ran it, right? 1 million? There we go. We're not going to be sitting here waiting for 20 minutes. This will actually execute in a blink of an eye, right, instead of 20 minutes, when we do this properly. We're going to do this properly on Wednesday. And as a preview of this, we already gave a preview before the break, but to remind ourselves what the preview looks like, let's take a look at selection sort again here. And remember that it's sorting in ascending order, right? 2, 3, 4, 5, 6, 7, 8, 9, 10, whatever. What would I do to change it to sort in descending order? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. What line would I change? This one right here. In fact, what character would I change? Greater than. That's it. Now, of course, it's not min index. It would be max index, but that's just a variable name. Who cares? Call it X if you want to. Right? All I would have to do is change this one character. All right. Well, what if you, instead of integers, you wanted to sort an array of books? Right? What would you change? This right here. I would say compare the jth book to the min indexed book, right? And that's all I would do, right? That's just plain English. How would you do it? Remember what a book looks like. A book is a title, an author, a release date, a rating. Well, what do you mean by ordering a book? Which book do you want? Do you want to sort them in ascending order, descending order with respect to rating? Because you want the best book and the worst book? Right? Do you want to sort them with respect to author? Author's last name, first name, right? And then Asimov comes before Zebra or whatever, whoever writes books that starts with a Z, right? Or do you want to sort them by title so that you get the alphabetically first title of the book and then alphabetically last title of the book? Which one do you want to sort by? Every time you change your answer, all you need to do is change that one line of code. Do you need to change anything else? No, because all you're doing is going through finding the minimum with respect to title, finding the minimum with respect to rating, and putting it in the front. You're doing the same thing with a different criteria. So what we're going to do is we're going to fill in the blank here, right? We're going to fill in the blank with some other component. And that component is going to be a comparator function that you're familiar with already from strings. strcmp. CMP is short for compare or comparator. Given two strings, A and B, do they go like this? A comes before B. It returns something negative. Do they go like this? A comes after B. Returns something positive. Or are they equal? Right? They have the same values, so return 0, right? We're going to be writing our own comparators for that. But before we do that, we have to understand not only what a comparator is, but what a function pointer is. And that's what we'll do on Wednesday. Okay? All right. Have a good day.